All right, we're back. So what do we do? Quaternions. And we will see those in a few slides. Continuing with refreshing things, we should all know how to represent kinematics for a particle, of course. Velocity of a particle with respect to a certain observer, in this case is an inertial one, is given as the time derivative of the position vector with respect to the same observer. Acceleration is the time derivative with the specific observer of that velocity. You notice here that all these time derivatives have a certain observer specified. We all remember Galilean transformations. If you are looking at two different observers that translate, rotate with respect to each other, the velocity seen by the inertial one that we call the absolute, if you want, is the velocity seen by the B observer, the moving one, which would be this raw dot of the point mass. And then you have the cross product of the vector rho and the angular velocity of the moving frame or observer with respect to the fixed one, and then the time derivative, of course, of how the origin is moving. The origins are moving with respect to each other. Much longer expression for the acceleration. You have the acceleration A seen by the inertial observer for a point mass P is given by the acceleration of the origin of the other basis. This term omega dot cross rho, again, rho is the position of the point mass we're looking at with respect to the origin of the moving basis. Then we have this double cross product, omega cross rho, which is what we usually call the centripetal acceleration. The acceleration that is the relative one, in other words, is the one that the observer attached to Fm is measuring for P. And then you have this cross product of the relative velocity, rho dot, of the point mass m, seen by m, I'm sorry, with 2 omega, and which is what we call the Coriolis acceleration. So no surprises there. This is just, breaking down those terms as I commented before. You're more than welcome to go through those by yourselves. Now, that was all kinematics. What we done in the previous slides is refreshing, how we represent velocities, accelerations, and in particular angular velocities, and how we connect the angular velocity with other angles, etc. So that was kinematics. Kinetics. Well, we need to remember that everything we do is based on Newton's laws. The inertia, a particle continues to move at a constant velocity if unperturbed or stays at rest. F equal ma, second one. Always keep in mind that that is true in an inertial reference frame, which is a reference frame, with the directions of the coordinate axis pointing at fixed stars. We don't really have a way to define an inertial reference frame that is very rigorous, but it's basically is any reference frame where F equal ma works, and it may be okay in your room for a short amount of time for your experiment. And then action-reaction principle, of course. The kinematics representation that we looked at before, the one that connects the absolute acceleration with the relative one, if you multiply both sides times the mass times the inertial acceleration is force. And so you can call everything that is on the right-hand side of this longer expression for the acceleration, you can call them forces. And we call them apparent forces, but really they're just an artifact of having expressed the acceleration of a point mass in a non-inertial basis. That's why all these terms come out. But really the Coriolis force, the centripetal force, etc., they're not actually real forces. They're not coming from a gravitational field. They're not coming from anything pushing against the object. It's just the fact that you are in a non-inertial basis measuring what's going on. And so if you are in a car taking a tight turn, you may see a centripetal force acting on something on the seat of the car that tends to go outward, but it's just you actually accelerating. So there's really no real force acting on it. It's just the fact that you are accelerating. But anyways, It's just good to refresh that people call these terms here mass times, for example, 2 omega cross v Coriolis force, for example. I mean, it's something that you, I'm sure, have seen before. And now, for our purposes, it is very important to know Euler's law, the one that has to do with angular momentum. So yesterday I asked if anyone was unfamiliar with the concept of matrix of inertia, and I'm assuming that no one said anything, so you know what it is. So each rigid body, each body in general, for each body we can compute what we call the matrix of inertia. Is the equivalent of the inertial mass for rotation purposes. He collects into a matrix values that tell you how the mass is distributed about the center of mass with respect to the center of mass, and how that is distributed will give you different behaviors in terms of rotation. So we know that the angular momentum of a rigid body can be expressed as the product with respect to the center of mass, so C is the center of mass, as the product of the inertia matrix J times the angular velocity of the body applied to the angular velocity of the body with respect to n is the inertial observer. So this vector that I call omega bn is the angular velocity of the rigid body, this potato here, which will be our spacecraft eventually, projected in xyz on the body itself, b1, b2, b3, so that's the vector. And J is the matrix of inertia also computed with respect to the axis of the spacecraft itself, of the rigid body itself. Okay, so once we have that vector, Euler's law will give us three scalar equations. Euler's law is really the first and last terms of this equality here that you see. Rate of change of the angular momentum vector of the rigid body with respect to the center of mass computed by an inertial observer. The rate of change of this vector equals the external moments acting on the rigid body. So these are torques or forces that are not applied to the center of mass. Everything summed up is the external actions rotation-wise that are acting on the rigid body. And so the fact that I have a intermediate expression here is just because I'm using the transport theorem. We just defined it in the previous hour. Why? Because, well, usually we're sitting on the spacecraft and we are measuring the angular velocity, as I said, with some devices of the spacecraft with respect to the inertial observer, but that vector will be projected in B1, 2, and 3. So I will have the luxury of measuring omega x, y, and z. And I will definitely have the matrix of inertia expressed in the body axis of my spacecraft. When you build a spacecraft, you model it in SolidWorks, for example, or you run experiments, but you definitely have that matrix expressed in a basis that is attached to your spacecraft. So in other words, my H will be most likely expressed in a basis that is B1, 2, and 3. But I have to take the rate of change with respect to some other basis, which is the one attached to the inertial observer, I1, 2, and 3, and so I use the transport theorem. I can use it for any vector. So rate of change of H with respect to n is the rate of change of H with respect to B, and B is the spacecraft, plus the omega of the spacecraft with respect to the inertial observer, cross H itself. No surprises. Now, if you take this vector expression and you project it on each one of the axes of the satellite, B1, 2, and 3, you get these three scalar expressions. So these are the usual expressions that you see when you talk about a rigid body moving in space, rotating in space, acted upon generic moments. So mcx, mcy, mcz are the moments, external moments acting on the rigid body with respect to the center of mass. Okay, and the matrix in general is non-diagonal. This matrix of inertia, J. So it has terms of on the diagonal axis, on the diagonal itself, and then it has terms off diagonal, and that depends on how you choose your axis to compute it. These quantities. Let's see if I have an expression that represents, for example, Yes, one of these J's. These quantities in the J matrix are nothing more than distances squared integrated over the mass, the entire volume of the object. So to do that, you have to choose a certain basis. And so we usually start with some symmetric axis, depending on the design of our spacecraft, but then you can always diagonalize this matrix. And in your folder, you have a lecture 2 diag inertia matrix function. It's just an example that you can run, and it takes, it's opening now. Well, it just takes this matrix here and it diagonalizes the matrix. So if I run this in the workspace, I start from a J matrix that is just, you know, a non-diagonal matrix. The first instruction computes, let's see, what is the first instruction? I don't remember already. Well, actually, it's the EIG command in MATLAB. It will compute the Eigen values and let me see, the Eigen values lambdas and Eigen vectors E for the matrix J, and through the last operation, which is diagonalization, pre-multiplying times the matrix that contains the eigenvectors transpose, and then post-multiplying times the same matrix, you get the diagonal version of J. So this matrix is just the same one as the original one. It's just that now it's expressed in a new coordinate system, which is the one of E. So here I have computed, for example, the matrix of inertia with respect to some coordinate axis attached to my spacecraft. Then I compute these three directions, the eigenvectors of this matrix, and this give me the direction of what we call the principal axis of inertia of my spacecraft. And so with respect to this axis, the moments of inertia collapse to only three values on the diagonal. As you can see, these three values reappear on the diagonal of this matrix, and you have no off-diagonal terms in this new coordinate system. So it's just basically diagonalizing the matrix of inertia is an exercise you do to find new axes with respect to the ones that you originally defined, in which the matrix of inertia is just simpler. And so when you find that basis, your vector Aureus law in the three-body axis collapses to these three scalars where you, as you can see, you don't have any off-diagonal terms. You don't have the terms JXY, JZX. You don't have any of those. Only the JYY, JXX, JZZ. So the three principal moment of inertia of the spacecraft. And of course, you have special cases where there are other symmetries. For example, you know, two of these moments of inertia may be equal, and so these nonlinear terms go away. But basically, these are the three equations of motion for a rigid body, and these are the equivalent of F equal ma, nothing more, projected on the three axes. In the case of a point mass, you have the linear acceleration, A. Here you have the angular accelerations. You have the dots on top of the omegas. So, all right. So properties to be remembered of the inertial matrix. It's very important. It does depend on the geometrical shape and distribution of the masses, of course. They do depend on what Cartesian reference body frame you've chosen. We just looked at that. You can diagonalize. They're called, the ones on the diagonal are called the main moments of inertia, and they're always positive or zero. The off-diagonal terms, if you haven't diagonalized your matrix yet, called products of inertia, are either positive, negative, or zero. It is a matrix that is always, of course, real and symmetric. If you get an inertia matrix that is not real and is not symmetric, it's not an inertia matrix. You're not talking about an actual rigid object, a physical, meaningful object in reality. It is positive definite, which means that all the eigenvalues are real and positive, and they better be, because when I diagonalize my matrix of inertia, I need to find the principal moments of inertia, and at point 3, I told you that they're always positive or zero. There are some inequalities that also hold. So the above properties are not enough. The following three expressions also have to be respected to be a proper matrix of inertia. And you can, just look at them. They're just constraints and inequalities that need to be respected. If you do a permutation of 6 of those, I'm sorry, if you do a permutation of the subscripts of this expression, you get 6 more inequalities. Which means that basically when you give me 3 elements of J, 2 on the diagonal, the other ones have to stay within certain ranges. So bottom line, you can't just choose any real symmetric positive definite matrix and call it an inertia matrix unless these other constraints are respected. A few more things. There is something called the translation or parallel axis theorem. If you have the matrix of inertia in a certain basis and you want to move to a new basis that is exactly the same in terms of the direction of x, y, and z, but is a different center, well, this is the way you do it. Basically, these are the way the single individual elements of the matrix change, where R is the vector that connects the initial center of the basis origin to the new one. If you're rotating basis, well, it's just nothing more than a rotation matrix you need to apply to J. The principal axis of inertia, they always include the axis of maximum and minimum moments of inertia. As you can probably imagine, once I diagonalize my matrix, I get 3 values, and one will be the maximum, one will be the minimum. For a solid of revolution, the revolution axis is one of the principal axes of inertia. If there are obvious symmetries, not only geometrical, they also need to be mass distribution symmetries, well, their axis of symmetry is a principal axis of inertia. If you have a symmetry plane in the body, again, symmetry is geometrical and of mass distribution, 2 of the principal axes are on the symmetry plane. These should be pretty obvious statements. And principal axes exist for all bodies. And so if you have some symmetries, it's just easier to find them. And here I have just some notable shapes and their matrices of inertia with respect to the principal axis. If you have a spherical object, uniform mass distribution, obviously any axis of inertia are principal, as long as they go through the center of mass. And these are the 3 values, identical, obviously, for the moments of inertia. If you have a cylinder, obviously and everything is homogeneous mass distribution wise, the axis of symmetry is one of the axes of principal inertia, and any other 2 normal to that and normal to each other are also principal axis of inertia. And these are the values you get. For x and y, of course, they are identical because they are because of the shape of the object, and the one about the z-axis is different. And then for a parallelepiped system or object, this is what you get. You can find them online. You can find many different shapes, and you can combine them together. If you have a cylinder with a sphere attached to it at a certain distance, then you can find the final complete moment of inertia of your spacecraft. If that's what it looks like, a cylinder with attached a ball on top of it, well, then you will have to bring everything to the same center by using some of these theorems, for example, and compose the final assembled matrix of inertia. But it's nothing special. Additional notes on angular momentum and J. The angular momentum and omega are not usually directed in the same way. I'm going back to this slide here, slide 16. See here, HC and omega are on purpose pointing in different directions. And that's usually the case, unless you have a very special J where you have a diagonal J and the values on the diagonal are all the same, in which case it's just a rescaling of omega through this expression here, H equals J omega, but that's rarely the case. There are 2 different vectors. You obtain H by pre-multiplying omega by a matrix, so the H will be in general different from omega. And these are obvious things, but I see this error made over and over again by students because we tend, and also not only students, professors as well, we tend to jump to conclusions and simplify things, but special cases can be simply represented by expressions that collapse into parallel vectors, but in general that's not true. If omega is though, about one of the principal axes, if the angular velocity is happens to be about the one of the principal axes of inertia, then they are parallel, and you can just quickly show that to yourself. What moments of inertia represent, as you can imagine, they represent resistance to changes in omega. In other words, to angular accelerations, the same way as mass represents, inertia. Changes, the more mass you have, the harder it's going to be to change your velocity. Well, go back here. The more J you have, the harder it's going to be with your external moments to change H and in turn omega. So that's really what they do. It's just a very ugly, non-linear way to look at things. F equal ma is a lot more, it's a lot easier to deal with, but that's really what they represent. Just to give people an idea, because we're engineers, we need to be, used to numbers. If you look at a human body, let's see, the vertical moment of inertia is usually 0.5 kilograms meter squared. Of course, that depends on your size and weight and etc. For the other two axes, they're kind of similar. It's about 20. And to give you an idea of moments, torques, if you need to open a door handle, you usually apply a torque of 15 Newton meters, which, if you go back to the tables that I showed you yesterday, is definitely not a negligible torque. It will do a lot in space for a satellite of reasonable size. You will change its orientation pretty quickly, actually. So, how are J's measured and estimated? As I mentioned before, you design your spacecraft, and that's the first step. Usually, what you do is you have a SolidWorks file. You try to model all the components as accurately as possible with the materials and mass distribution and where they are located, and you have a first estimate in software of the matrix of inertia, and that's what we do in my group. Then there are experiments, turntables, load cells. So you spin objects and you try to measure the direction of the principal axis and their bodies. When you go to balance the wheels of your car, and they start adding those weights in different locations, that's exactly what they do. They spin them to measure the location of the principal axis of inertia, and they adjust that until it's kind of centered with the geometrical center of the wheel. And then there is also an orbit estimation. The Cassini probe had a software on board that allowed for the during flight on orbit estimation of the spacecraft's inertia tensor. So it's definitely a system identification problem that is not trivial to solve. Okay, now you know that in this class we have a couple of homeworks. Really, the last one is the most important one, but the idea is that we start building incrementally this final assignment. So the first assignment that I'm giving you here is not the entire homework one, but the first step is that you take Simulink and you code Aureus Law and the 3-to-1 Euler angle kinematics that we have seen. You can choose any matrix of inertia, same as initial conditions, then we'll change them. So in other words, I would like for you to code what? These three equations right here, and generate a function that outputs the angular acceleration so that you can numerically integrate omega x, y, and z given initial conditions for omega x, y, and z. And basically, let's see, let me go back to these images. And the other equation, differential equations that I would like you to code is this one. It's a function that spits out the rates of change of the three Euler angles, since you have omega coming from that other set of equations, with the sequence 3-to-1. So it's equation B1 here, where B is this one, table B3, the last one, 1 over cosine, etc., etc., okay? So that is the first thing that I would like you to work on as soon as possible, really. And the question now is, would you like me to start looking at this together now? We have another hour and a half today. And so maybe take a break from these slides and theory, or you want to continue with theory? I know that the choice after all is mine, but I think we can probably start looking at Simulink. I think it's probably a good idea. Okay, so let me see what we have here. Okay. So I do actually have an already developed homework 1 Simulink file if it ever decides to open. Yes. Okay. So this is to give you an idea of what I would like you to build. The first question in the slides is implement the Euler's law in the scalar form in Simulink. And this is exactly what I'm doing here. So go back to my camera. Okay. So what is that equation right there? That equation is omega dot, and this is in a vector form, right? Equals inverse of j, so j minus 1, and I have that multiplying minus the cross product of omega and j omega. This is a matrix, this is a vector, plus t is what I called moment before, t torque, m, same thing. Okay, vector. So this, I'll go back to the slides, is actually, well, I guess I lied. I said that I wanted it in scalar form, but I'm just writing this expression here. I don't know if you can see me highlighting it. It's dHc with respect to b, with respect to dt of hc with respect to b plus omega cross h equal external torques. It's that equation where h is actually expressed as j omega. So the first term is j omega dot, because this dHc dt with respect to b is the rate of change of this vector as seen by b, and what is changing in b is only the angular velocity, right? Because this vector hc is expressed in b. So j is not changing, the matrix of inertia is not changing in the basis b1, 2, and 3, because I have expressed it in that basis, and it's fixed in that basis. Omega can change, and so the rate of change seen by the observer that is attached to the spacecraft, or h, is only j omega dot, right? But then Euler's law tells me that h should actually be taken the time derivative of with respect to the inertial observer, so I have to add with the transport theorem this cross product. And so that's what my expression here on the piece of paper is doing. It's basically starting from, this is where it's coming from. It's coming from dHc in respect to b plus omega bn cross hc, okay, equals, let's call it t, okay, just because that's what I have in MATLAB. So this first term, since h, I expressed it as the matrix j times omega b with respect to n, okay? This first term is j omega dot, correct? The observer that is attached to the spacecraft doesn't see j changing, but he can see omega changing, and then I have omega Bn that is crossing J omega Bn, and this is equal to T. All right, so all I'm doing then, well, dropping all these B and N and all the symbols, going here is just inverting, solving for omega dot, okay? Nothing more than bringing this to the right-hand side. That's why you see that minus omega cross J omega plus T, and inverting J. And we know we can invert J because of the properties that we've seen before. So that's how I'm writing Euler's second law in MATLAB. Why am I doing it this way? Well, in Simulink, you always want, if your goal is integrating differential equations numerically, as we will do here, you always want to isolate the highest time derivative you have in your differential equation and bring everything else to the right-hand side, because that's how you build your function. So if you look at this function here, it is taking as inputs everything that I see on the right-hand side. On the right-hand side of my expression, I have omega, J, and the torques, external torques, and the output is omega dot. So this is in general for any differential equation in Simulink how you want to do it. The output of this, so this block in Simulink is taking as input the angular velocity, is taking as input your J matrix, whatever that is. It's taking as input your external torques, whatever they are. In this case, I'm just giving 3 zeros. And it's spitting out the omega dot. The omega dot allows me to take the block in Simulink that is called numerical integrator 1 over S. I specify here an initial condition. I called it OM0. I'll show you what those are defined in a second. And numerical integration of omega dot gives me what? It gives me omega. And so I feed that back into the block itself. So this is how a numerical integration really occurs in Simulink. So forget about these other blocks, but really they're doing the same thing. They are integrating different differential equations. This one is integrating Euler's second law, given some initial conditions that I'll show you in a second. So where do I find all these ingredients? For example, these numerical integrator, you have the library browser, whenever it decides to open. Maybe. Okay. Cooperation with Simulink. Okay, so when you click there, after some time, this is what opens. And so, for example, if I want to numerically integrate something, I search for integrator. Can't write today. Of course, it's not going to find it. I misspelled it. Super fast today. I don't know why. Anyways, search for integrator. Eventually, you will see among the other options that 1 over S. Yes, right here. There are different ones. Discrete time. This is continuous time integrator, etc. So that's how I enter it. You just grab it, drag and drop. Oh my goodness. Okay, it did it eventually. Let me destroy that. Of course, the library went away. These other ones are MATLAB functions. This is a MATLAB function. So you search for function here, you'll find all these different blocks and utilities in the library. Then one thing that I'm doing, you've noticed that I'm calling J, this is a constant, and it's just called J, but there are no numerical values here. Here I manually enter the vector of zeros, but also here in the numerical integrator, the initial conditions is symbolic. It's a variable, but there's no numerical values. Well, because I've defined them into a MATLAB file, and this is a very convenient way of doing things that I call initialize. And so forget about all these other values that for now you're not using, like these gains. This is the final time for the simulation. Well, this is the J matrix that is using. Forget about ISW and Y for now. But this is the matrix of inertia that is used. And this is the initial angular velocity that is used. ohm 0. It's in RPM, so 555 would be in RPM, and then this operation transforms it into a radians per second. So how does Simulink know that he needs to use that MATLAB file where all these initial values are defined? You go to modeling, model settings, properties, callbacks, init function. You just type in the name of the M file. So when you hit run for the Simulink model, it will first run this MATLAB file. And then I have also a stop function that, in this case, I'm not calling a MATLAB file. It's just plotting in 3 figures a bunch of values here. So you could copy these and put it into another M file and call that file. I just typed everything here for some reason. It's just another way to run something at the end of the simulation. And so, forgetting about these other blocks, if I run this, hopefully it won't crash. It didn't like that. Error evaluating callback string is initialized. I may not be in the right folder. And that's exactly what's going on. I'm not in the right folder, so it doesn't see that file. Let me see. Here you go. So now it should work. I run this. It's compiling. We should run this for 1,000 seconds and then plot whatever I asked it to plot. Yes. So it's on my other screen. Let me see what I want to look at to begin with. Okay. So this is the angular velocity behavior given no external torques, those initial velocities I gave you, and the distribution of mass that I gave you. So this is what omega is looking like. Questions? Okay. So and that's the first thing you should do, something that looks like this. Then the second block, the second part of the assignment that I defined in that last slide is the order angle sequence 3, 2, 1. Well, it's another differential equation. It's the one from the textbook. Again, going back here, is equation B1 with the correct B matrix, which is this matrix right here. So that's exactly what this is doing. The B matrix is assembled by having as inputs EA. This is a vector with the 3 ordered angles. So the first component of the vector is theta, then psi, and then, phi, theta, and psi. And so I put together B according to the textbook, and then my EA dot, so basically phi dot, theta dot, and psi dot are generated by multiplying B times omega, exactly like in that expression from the textbook. And so this function here generates the time derivatives of the ordered angles, and I integrate those numerically. I gave them initial conditions that are defined in the same file that I showed you before. They're called EA0. Let me see if I can show you that file. Initialize, I don't know what they were, right here, 0, 0, 0, just 0 initial order angles. And let me see if I can find the plot. Of course, it's a bunch of plots that I mixed up. Okay, this is what I get for order angles. The first one goes up indefinitely, and no, I'm not wrapping it up every 2 pi, so I just let it grow. I could do that. The other two are staying a little more limited, and they're oscillating and changing values. But this is what's going on with those 5 RPM per axis at all times. Oh gosh, I wanted to zoom in, not this. Yeah, let's see what's happening to these other angles. You can zoom in and look at them. but that's what they look like. And this is, it's an example that doesn't have any particular physical meaning. It's just, an exercise to integrate numerically the differential equations. Okay? Any questions on Simulink? No questions. So what I really want you to do is to basically build. Oh, and one thing to notice, now that we have Simulink open, notice that omega is also coming into this second function, because without omega, I wouldn't be able to perform the last operation, which is the product of the B matrix and omega itself, of course. So as you can see, the kinematics block, this one, needs the information from the kinetics block. So if I didn't have the Euler's equations, and these are the equations of motion that give me an explanation of why omega is changing the way it is, and the y is, in this case, the distribution of mass J, and the torque that is coming in this case, a bunch of zeros, but it could be something else. So that's kinetics, and that allows me to generate the angular velocity behavior that feeds the kinematics. So from the point of view of what's causing the motion, this block doesn't care. This block only needs to know, the Euler angle block, is what omega is doing. As long as you feed it omega, no matter why it's behaving that way, it will be able to tell you the time history of the Euler angles. Okay? Other things to notice about this is I'm saving also the variables into the workspace if you need to do anything with them, omega and EA. But really for tomorrow, as soon as possible, I would like you to have these two blocks, this part basically, forget about the last part, which is Quaternions. We're going to talk about them today. But for next time, do these two, okay? And you can choose my initial conditions if you like. I'm recording the lecture, so you should be able to really, if you want, use the same J. It doesn't matter for now. So this is the J that I'm using. This is the omega 0 that I'm using. This is the initial Euler angle that I'm using. That's it. That's all you need for this. Okay? So the silence, yes. What's up? Question?
So, Professor, is this for tomorrow, not for later?
No. I mean, I don't want to be pressing anyone with deadlines. I'm just suggesting for tomorrow. I'm just suggesting that you start getting this, working on this as soon as possible, really. Okay? Yeah, I'm not going to check that you've done it tomorrow, but hopefully you will have something ongoing sooner rather than later. I think for this class, since we finish Wednesday next week, I don't know how you usually, the University of Naples runs these courses, but I'm fine with you working on the Simulink final assignment, even, past Wednesday, if that's something that works for you guys. It doesn't have to be all done by Wednesday, as far as I'm concerned, if that's okay with you. Okay, that means yes, probably. Okay, so basically, yeah, this is the start of homework 1. We'll add more things, but code the Aureus Law, the kinetics part, and the 3-to-1 sequence kinematics part in Simulink for, as soon as you can. All right, good timing. I think we can start looking at something else. Very quickly, and then we'll stop in a few minutes and resume. We have another hour today later on. I think it's your 6 p.m., right? Okay, so we already talked a lot about we parameterize orientation, right? Now we start getting a little more visually meaningful. Here I have a 3U CubeSat with its body axis, and this is the observer. Go back to what we just discussed. This will be your B axis. Remember B1, B2, B3 if you like, and this will be your A1, A2, A3. So we really want to represent how this object is oriented with respect to A. And we have seen the DCM, and that's the way to do it, as we said. There's really no issues, no singularities with the DCM. You're just taking a bunch of unit vectors and you're projecting them on another bunch of unit vectors. But then we've also seen other angles, and they're kind of nice because it's 3 of them instead of 9, and you can kind of visualize them because they're angles, they are rotations. We can split things into 3 single axis rotations and assemble the angular velocity with the chain rule. So there's a lot of advantages, except they can become singular. But we want to express orientation of a frame with respect to another because we want to be able to transform vectors between the two. We want to express the angular velocity, as we've done, as a function of orientation and time. We do not care really if they share the same origin. That doesn't matter. When I define the ordered angles, you know, for convenience, I was drawing things in with the same origin, but it doesn't matter. What really happens in reality, what is called strapped down inertial reference systems, is that the body rates, as I said before, the angular velocity, omega, x, y, and z, are in the body axis of the vehicle. Ordered angles, unfortunately, have the singularity problem. They degenerate. You have cosines or a denominator. The issue is that you're representing the same rotation with infinite values. We discussed that, and so we want to do something a little bit better, okay? And that's when we start talking about quaternions. Assuming that many of you have seen them, but you know, we'll cover them again, very high level, and in a practical way for immediate use. You know, quaternions come from, first of all, a theorem that is called Euler's Eigen axis rotation theorem. If you have a rigid body that is rotating, you know, you can change the orientation of the rigid body from an orientation A to an orientation B by individuating an axis in space that is fixed in the body and also with respect to the inertial observer, and an angle about that axis. This is called the axis of rotation, and it's called also the Euler axis or Eigen axis, because basically this axis E, we call it E, is the same as the same projections in A and in B, in the body axis and in the axis of the observer. So basically, going back to this image, has the same projections here and here. And so basically, if you apply the rotation matrix, the DCM that goes from A to B to the axis E, you get the same axis. So is the eigenvector basically of CBA, corresponds to the eigenvalue 1, and so the fact that there is this theorem that we're not going to prove, that any orientation from a certain configuration to another can be represented with a rotation about that axis E and an appropriate value theta, rotation angle theta, is the basis of putting together an alternative to Euler angles, which are called Euler parameters. Quaternions are just one of the many possible combinations for Euler parameters. And what they really do is they take the E axis, the eigenaxis, and the value theta associated with that eigenaxis, and shuffle them together, combine them together in a way that represents the DCM, nothing more than a DCM. Always remember, everything we do will boil down to representing the DCM, just in a more convenient way. Euler angles are a 3-parameter representation of the DCM. The quaternions and Euler parameters are a 4-parameter representation of the DCM. So we add one more to solve the problem of singularity, basically. So introducing quaternions, developed by a gentleman called Hamilton in the 1800s. There are also different versions of quaternions that you can find out there. But one of them is you take the Euler axis, E1, 2, and 3, multiply those components times the sine of the angle theta, the rotation about the eigenaxis over 2. And then the last, so you have the first 3 components that are basically giving you a vector. And the last one is a scalar, is cosine of theta over 2. So again, what is this E and theta? They are telling you that your object, this spacecraft, at any given position in terms of orientation in time, you can represent that orientation by an eigenaxis that changes with time, of course, and a rotation theta about that eigenaxis. Instead of using DCM or other angles, it's just another way. You can find an axis that respects this relationship, E equals CBAE, and an angle theta, and wherever your object is pointing can be represented by E and theta. And here we're combining them together in this form, okay? Now, properties. Well, first of all, a quaternion has always the norm of 1 because of the way I have constructed it. As you can imagine, the norm of these first 3 components is sine of theta over 2 squared plus cosine squared is always 1. And without proof, because it's a tedious process and it's something you find in textbooks, you can show that the DCM, or the rotation matrix from B to A, in terms of quaternions now can be expressed that way that you see in this slide. It's ugly, but there's no sines, there's no cosines, there's no divides, there's no way that you can get a divide by 0 in that CBA. And there's no trigonometric functions really. So if I give you a quaternion, you can put together a CBA according to this expression. If I give you a set of other angles, you can put together a DCM like we've seen before. It's the same DCM. So you start seeing that there is obviously a relationship among all these different representations. Obviously, they are just different coordinates. You can always go from a system of coordinates to another one. And you do that always going through the DCM. So if I give you other angles and I ask you to compute what are the quaternions that correspond to this orientation that I'm giving you in terms of other angles 3 to 1, first thing you do is that you compute the DCM. And then the DCM is what it is. It's a matrix of 9 numbers. And that matrix, it can be used in many ways. And one is, well, now I want to back out the quaternions. And these are expressions to do it. So the DCM in terms of quaternions is given by this formula. I personally refuse to memorize these expressions. You should not, obviously. I mean, they are available for you. If you want to extract a quaternion, there are different ways. The fourth component of the quaternion is given by the trace of this matrix. So basically, you add in the diagonal terms plus 1 square root divided by 2. And then the vector component is given by this other expression. Now, what happens if Q4 is 0? Well, there are other combinations, other manipulations you can do with these components of the DCM to extract the quaternion. And I am giving you the function that does that as well as in your folder for today. So I call this DCM to quat as quaternion mine. Why do I call it mine? Because I took this function from the aerospace toolbox. I do have a license. You may not have that. So very simply, you just open that function, call it something else, and here you have it. So this is just the aerospace toolbox function that takes a quaternion, a DCM, as you can see, takes a DCM and spits out the quaternion. And it has a bunch of if-then else's here. They take into account the fact that that fourth component could go to 0, and so it's basically using the elements of the DCM in a different way if that happens, so that in the end you have your quaternion. Okay, that's all you need to know. Again, it's in textbooks, but it's nothing more than these two expressions here with alternatives in case Q4 becomes 0. All right. So here are your quaternions. What are the differential equations? Now, the kinematics equations in terms of quaternions. Well, we'll see them later this afternoon because I noticed that it's already 11 a.m. for me. Okay? So we're taking a break, guys, and I will see you in 2 hours.
Okay, thanks.
Thank you. See you later.
Thank you.
Thank you. See you later.